Right. So, this is what it is. Now, I said it's a self-reacting system. What is the meaning of self-reacting system, right? So, pre-stressing is applied in post-tension system by jacking against the member, and the eccentricity is easily varied along the length of the member. Please note that in the pre-tension system, you remember to keep the cable at a particular profile, we need to have some deviatoric system. We also applied some vertical pre-stressing through cable which was held at the bottom. So, you need lot of external devices to keep it there. But in case of a post-tension system, you have to basically create a duct in the mold, and if the duct is held in position, that is what it is going to house the pre-stressing steel. That will in turn will give you the eccentricity that what you want. So, it is very easy for us to create the profile, PT cable profile easily in a post-tension system compared to that of pre-tension system. In pre-tension system, typically straight cables are most commonly used, but if you want a linearly varying cable profile, you need to plan for it, and then it's quite involved, right. Now, in post-tension system, as we said, this is an anchorage block, right, and then you have this is your duct, okay, that you keep it inside, and this light color element is nothing but your PT cable, right. So, now once all the concrete is done, then you take the jack is going to push on this concrete while you are stretching the cable. So, that is why I said it is a self-reacting system. You are pushing the concrete member itself to apply the post-tensioning system. Now, this is a dead end usually, and wherever the hydraulic jack is there, it is called as live end, okay, and this is the duct. Now, once all the pre-stressing is done, then you go ahead and close the duct with the gap that you want. So, the steps are place the reinforcing cage and post-tensioning ducts inside the formwork. After casting and curing of the concrete, the tendons will be tensioned and they will be anchored with special jacks that are going to react against this member. Unless unbonded tendons are used, the duct is going to be then grouted to complete the post-tensioning operation, right. Now, this is a very interesting example of a bridge almost 102 meter length, which is called Sant Dhyaneshwar Palki Mahamarg in Maharashtra. Very recently, only in June, I think they have completed and they have opened it up. It is the longest single span bridge against a canal, which is 102 meters, single element. In fact, if you look at the size of the element, it looks basically like a steel girder with a very thin webs. This was made using special ultra high performance concrete of strength 160 megapascal, and you can see such kind of elegant systems can be done using post tension. In fact, these individual U-shaped girders were made using match casting, and then they were all connected together through post tensioning cable, and then they are post tensioned to form this one single unit of 102 meter length span. Now, these are the examples. So, let us go through what are the stages involved in post tensioning. So, as I have explained, as you can see in this animation as well, in the stage 1, cable ducts and reinforcements are positioned in the beam mold. Then the ducts are usually raised towards the neutral axis at the ends to reduce the eccentricity of the pre-stress. What do you mean by? So, this is what it is. Here usually the eccentricity is going to be high, and here it is going to be close to the CG of the cross section. As we have seen, you also splay it little bit so that you can reduce the stress concentration while you stretch it. And then in stage 2, concrete is cast into the beam mold, and then they are allowed to cure to gain the initial strength. In stage 3, once the concrete is cured to sufficient strength, then the tendons are threaded. So, basically tendons can be inserted, usually they are inserted after concrete is cast and it is cured, then you needle the thread through the duct, and then they are usually tensioned about 70 or 75% of their ultimate strength. Then wedges are inserted into the anchorages, and then tensioning force on the tendon is released. Okay. So, and the anchorage blocks again, while you jack it and then you wedges are inserted into the ends of the anchorages, and then the tensioning force on the tendons will be released. Then if you want a bonded system, grout will be pumped into the ducts to protect the tendons. This is mostly, pre-stressing steel is more prone to corrosion than a normal steel because it's a high energy material. During the manufacturing process itself, we are putting a lot of energy in the manufacturing. So, it is tend to corrode faster than a normal steel. So, you need to protect the steel. So, that is why grouting is usually done in case of a bonded system. In unbonded system, again, if you are not careful, if you are allowing a ingress of moisture, chlorides, then the possibility of corrosion is going to be higher. So, we need to be very careful with that. Okay. So, this is another example of how do we do the tensioning for a 2-span continuous girder, that what you see here. And you see here the cable profile, actually the cable profile should follow bending moment diagram, what you are going to get from your external loading. The bending moment profile, if you know for a particular load what kind of bending moment that you are going to get, then the cable should actually follow that bending moment profile. So, that is why you see here at the bottom you have sagging moment. So, that is why you have eccentricity of the cable at the bottom. Then at the top, at the support locations, you have hogging moment. So, that is the reason your eccentricities of the cable is above the CG. And then again at the midspan, you have sagging moment. So, that is the reason the cable again comes down and then it goes up like this, right. So, it follows closely the bending moment profile. And we also, for this example that you see here, you have total 6 cables of post tensioning cables are there, and we try to do the tensioning in a sequential fashion. Okay. So, that you induce the correct type of stresses that what you want, right. So, this is the way that we do. So, first cables are done, second cables are done, third cables are done, right. Then while you do the grouting again, so you typically you do it from 2 ends. You see here the reason why we do the stressing, if possible, if you have access is there, it is always better to do the stressing from 3 cables from one end. Let us say if you have 6 cables in the system, 3 cables are stretched from one end and the 3 cables are stretched from the other end. In this way, you get average level of pre-stressing force. When we talk about losses, especially in post-tension system, friction losses can be quite significant. So, to reduce the amount of friction losses, typically we try to do pre-stressing from both sides if possible. If your site conditions allows you to do stretching from both sides, that is the best thing that we can go for. Then the next step is you have grouting process, because it is a bonded system, you have to do the grouting. Now, grouting again, this venting tubes have to be provided, otherwise what will happen is airlocks will form and then the grout will not be able to pass from one end to another end. So, then you will not be able to grout the entire duct very well. Then if you have gaps that are there, there is a high possibility that moisture and chloride can get into the system and then it will start the corrosion process. So, which we should avoid. So, that is the reason it is very important for us to have this venting tubes to avoid the airlocking, so that while you inject the grout from one end, the grout will flow nicely through this, it can come out on the other side. So, that is also we have to keep it in mind. Now, this is a very interesting application where you can also create a post-tension and pre-tension system combination, right. For example, these individual elements can be done using pre-tension, right, and then these 2 elements can be joined by post-tensioning technique. So, that is called splicing. So, or you can do this one particular location, you can do the side casting, and then after the side casting is done, if you have the access, then you can run the cable and then you can stretch the individual elements together. So, that is also can be done, splicing can be done using post-tensioning as well. Now, let us look about bonded post-tension system. And we have seen that post tensioning you have different types, bonded and unbonded systems, and unbonded systems are quite popular in India. In North America, they tend to use more of an unbonded system, but again depending upon the application, so we cannot generalize it, but unbonded systems are quite widely used in North America. But if you look at Asia and Europe, typically bonded systems are mostly used, and typically as we see, the tendon force is transferred to concrete along the full length of the tendon by bond. So let's look at now. So to create, after this tensioning process is done, we use the specialized cementitious grout system, and you can see that again the quality of the grout also has to be done. The flowability of the grout has to be tested to ensure that it is very flowable grout that you are having. Then what we do is the tendon is grouted through this anchorage blocks from one end to another end. Unless if it is a flowable liquid, it cannot really pass through. And this is again another example of a post tension cable system. For that is, this is a basically flat system, flat 3 cable system. These are commonly used for PT slabs, okay, because slabs are thinner elements. I cannot have a 12 cable or a 19 strand cable system. Typically they will have 3 strand or a 4 strand or a 5 strand flat systems that are used for slab application. So here also you see here you have anchorage block and you have the grips, wedges that we talked about, and then the strand comes through this, right, and then this is called as a, sometimes it's called as a guiding pocket, or it is also sometimes called as trumpet, and then it goes, and this kind of a bulbing, this process is called bulbing of strands. Bulbing of strands is done, and this bulbing of strands is basically, it will not let the concrete, the strand to come out of the system, and this is the way that you anchor this one end of the strand into the concrete. This is one type of end anchorage. So like that, multiple end anchorages are there. For example, in bridges, the end anchorage systems will be different. But the final point is this grout vent, the grout is poured through this, and then this is a venting tube. Okay, this is a venting tube, and we have to ensure that the grout passes through from one end to another end, it comes out from the other end. Once all this grouting is done, then finally the high tension steel is cut using abrasive disc cutters. Then you also put this kind of a cap, and this is very, very important. This kind of a protective end caps have to be placed so that the moisture, rainwater, other chemicals cannot enter. If the anchorage block zone starts getting corrosion, then the performance of the PT girder will be compromised. So we don't want to do that. This is like a weak link. So you have to make sure that the anchorage zones are very well protected with the end cap. Now again, the grouting of the ducts, let's spend some time because it's very, very important. If you are not using good duct system and if you are not using good grout, these PT cables can corrode faster. As I said, corrosion rate of a PT cable is faster than the normal steel. So here typically in grouting we use non-shrink grout or non-shrink admixture has to be used. Typically we also put anti-corrosive agents, okay, or also we use corrosion inhibitors also. For long girders, as we have explained in the previous slides also, we need to provide air vent to release the trapped air and ensure complete filling of the ducts with grout. For example, you see here, this is one example where I have a vent pipe and I am feeling that grout from one side. The grout comes from here and then goes all the way, right. If I do not have this kind of a venting tube, what will happen is while it is filling, you will end up forming this kind of air void. Now the air void, there is no physical contact of the cable with the duct because there is no grout. So again, if there is some element of damage, and then moisture can enter to the level of steel and it can start the corrosion. So to avoid that, it is always best to have sufficient number of vent pipes so that the air locking is avoided. Then we also have this metal ducts. Ducts can be of multiple types, but nowadays commonly what we use is a high density polyethylene ducts. Typically they are very lightweight, and it is also friction of this strand and this duct surface is also going to be less. Again, the friction is also very important aspect that we need to consider in our design, especially in losses, that we will discuss it. Previously, in the olden times, people use this galvanized metal duct, aluminum ducts. They are very popular use, but nowadays mostly we are using high density polyethylene. This flat ducts are used for again PT slabs, and these kinds of round ducts are used for variety of girder applications. Now again we talked about corrosion. Corrosion in pre-stress system can come from chloride induced corrosion, which is a major aspect. We can also have carbonation induced corrosion, and this is the duct that was taken out from a cable that was from a real bridge. You can see here that if the grouting is not done properly, and these are your strand, the strand will be left open, and you also see here if the grout is of not good quality, then you can have lot of this bleeding can happen, and then you also can have this segregated chalky type of segregation can happen, which will leads to this chalky type of paste material settling at one location, right, and that can lead to corrosion product forming very quickly. Okay, and you can also, this is again another picture, you can see a lot of air voids here in the system, and this is carbonation induced cracking, the corrosion that indicator. We do the phenolphthalein test to see the depth of the carbonation, and you can see if the grouting is not done properly, your durability will be compromised. Now, what are the common causes of corrosion? Moisture ingress. Again, if you have air gap on the strand, moisture can easily find its way through, and if grout is imperfect, then again you will have problem. And then concrete defects also can induce, and chloride or sulfate exposure also will create a lot of corrosion, right. And some of the commercially available corrosion products, corrosion inhibitors include Sika Ferrogard and Fosroc Aramix. All these corrosion inhibitors are actually added to the grout itself, and then it helps in reducing the corrosion in a grout system for a PT cable. Now again, this is one more example of in a bonded post tension system. You have this end anchorage block that was taken out, and if you see here, people have studied and they have divided this into different zones. Okay, if you see here, this is from zone 1, this is from again zone 2, and this is from zone 3, and this is from zone 4 and zone 5 and so on. And you can see here, what you can see, if the grouting is not done properly, and wherever you have high moisture content, for example in zone 1 you see here, this is a moisture content, the black color, and it goes like this. As it gets to 4th and 5th zone, the moisture content is less. The higher the moisture content in the zone, more the corrosion. That's what we see here in this region, the more the corrosion, right. And similarly, chloride also will play a major role in corrosion, and you can see this is a visual and chemical makeup of deficient grout at an anchor cap. Okay, this was taken at the anchorage zone. When you remove the anchor cap and then look at it and then do the chemical analysis, this is the distribution or concentration of all these chemicals in parts per million. So this unit is ppm, parts per million, and you can see here that higher the moisture and higher the chlorides, that is the location where you have more corrosion. So if you do the grouting properly and if you use a good quality grout, then the durability of the PT cables can be ensured. This we need to be very, very careful. Right. Now let's talk about unbonded post tension concrete. Now what is unbonded post tension concrete? The tendon is prevented from bonding to the concrete and it is free to move relative to the concrete. That means there is no physical contact between the tendon and the surrounding concrete in case of an unbonded system. However, the tendon force will be transferred to concrete only through end anchorages. They are connected only at the end anchorages. That is the key difference. In case of a bonded system, after grouting, at every cross sections you have connection of the PT cable with the grout and the surrounding concrete. However, in case of an unbonded system, you do not have that. For example, this is the way it is done. Usually these 7 wire strands will be there, and these 7 wire strands will be protected by this plastic sheathing, that, as we have said, this is a plastic. Typically it is done during the manufacturing process itself. They cover it with a plastic sheet. They do some extrusion process, and then they cover this coat, pre-stressing strand with the protective cover. Then in between, then you also can have a grease that will be put inside. These are all individual 7 wire strands. So this kind of a unbonded tendon system can be arrived. So this is an example of an unbonded cable that you can see here. These are typically individual cable, and you can also have a group of this kind of a system also. It is possible. 7 strand cable system or 4 strand system, depending upon what your applications, different products are available. But the key point here is this space is left with grease only, or sometimes they will be left unfilled also. So that is the key here, and only this. But between this plastic sheathing and the concrete again, because so that why do the, because the grease will allow the strand to move freely within the duct. Okay, so in that way it is basically it is free to move relative. The cable itself can move freely relative to the concrete. So that is the unbonded system. Now, what are the difference in terms of the force that you can apply? I mean, it is a cable, because grouting, while you do the tensioning, anyway grouting is done later, right? So post tensioning force, I can apply the same amount of post tensioning force whether it is a bonded system or unbonded system. But when you look at the ultimate condition, when the system is going to fail, when I am designing for an ultimate condition, I end up putting less rebars in a bonded system, right? Because I have strain compatibility, so I generate more stress from a bonded system than an unbonded system. So the reinforcement requirement in a bonded system will be less compared to that of unbonded system. Now, minimum core rebar, again there is no minimum requirement for a bonded beams or slabs, because everywhere you have strain compatibility. The concrete is in contact with the steel. So again, from shear reinforcement also there is no difference. Again, when we talk about flexural module, we will discuss in detail about all these things. But you get more efficient force transfer in a bonded system compared to that of an unbonded system. That is the point. Now let us look at this. Okay, this is what we explained. This is a beam with an unbonded system. For example, here I have a simply supported beam that is subjected to point load like this, right? And what kind of bending moment that we are going to generate? The bending moment profile is, again, it is going to be like this, right? Okay, and this you know that it is going to be WL/4, right? Bending moment, maximum bending moment. And you see here the strain in the concrete is going to follow the bending moment profile. But now, in case of an unbonded system, I have connections only at these two ends. In between, there is no connection of the steel with the surrounding concrete. Though the concrete is having a strain profile as that of the bending moment diagram, but steel, because it is not in contact with the concrete, it is actually having only average strain, okay, and epsilon Cp, average strain along the length, okay. Now, the strain in the prestressing steel is going to be always constant, okay, that is what it is. It is because there is no connection is between the concrete and steel is only at the support locations, right. So, if I take the average of this concrete strain, this is what we call that as an average strain, okay. So, the total strain now, because the system has to satisfy deformation compatibility, the overall stretching in the concrete beam and the stretching in the cable should be same. So, the net strain in the prestressing steel will become epsilon Cp average plus this epsilon P naught, which is basically your initial strain that you are locking in the system. And this is a compatibility condition. So, I have to calculate this in an average sense, because it's only having deformation compatibility. Every cross section you don't have the strain compatibility. Now in case of a bonded system, now concrete strain again, now every cross section now I have, again it will follow the bending moment diagram. We know that the bending moment profile is going to be like this. So similarly, the concrete strain profile also will follow. Similarly, steel also, if you see here, this is epsilon P naught, but this, because it is in contact with the concrete, this also will be the strain variation. The steel also will follow now the strain variation similar to that of your bending moment diagram, right. So this you can do direct addition, epsilon Cp plus epsilon P naught, that compatibility is there. What are the strain in the concrete plus the original strain that I am putting will be the total strain in the prestressed steel. But in this case, I have to talk only in terms of average strengths. So I have to somehow average the strain in the concrete. That average strain only I have to add to this. This is your initial strain, stretching strain, initial strain, right. That initial strain plus the average strain will give me the prestressing strain, steel strain in the unbonded system, but this I can directly add them. So that is the advantage. Okay, this is again in a stress strain curve. When you look at it at ultimate, this is at ultimate. So now what is an ultimate condition? When the concrete reaches epsilon C equal to 0.0035 as per IS code, right. At that condition, if you compare similar bonded and unbonded system, you will find that bonded system will be able to generate more stress compared to that of an unbonded system. Now why is it so? Because there is a strain compatibility at every section that I am taking. But in case of an unbonded system, because there is not physically in contact, I have only average deformation compatibility, I can say. In unbonded system, again deformation compatibility is satisfied at the member level. But here at every section, strain compatibility in unbonded system is not satisfied, but it is satisfied in a bonded system. So that is the reason unbonded systems are less effective compared to that of a bonded system. So if you look at the stress variation in the steel also, you will find that this is the way that you will have bonded system will have more stress. But in case of an unbonded system, it will be straight only. There will not be any variation with respect to bending moment. You have to take the average strain of concrete and add to that, right, that we discussed in the last slide. Okay, this is again an example of a two beams with same amount of prestressing steel, and you will find that at ultimate condition, bonded system is able to go as high as 1800 megapascal and it is able to give me 2450 kilonewton meter. However, when I same cross section, same everything, if I am having unbonded system, I am able to generate only 1420 megapascal at ultimate and I am able to generate only 1900 kilonewton meter. So you can see here the moment capacity at ultimate from a bonded system is higher than that of unbonded system, because I am satisfying strain compatibility at every cross section. So more stress I am getting out from the prestressing steel. Now again, advantages, as we have discussed, large reduction in traditional reinforcement requirements as tendons cannot de-stress in accidents. In case of an unbonded system, basically it is like a rubber band. If I go and cut somehow due to vandalism, somehow if we will try to cut the strand, then the entire force will come to zero. But in case of a bonded system, now that it is already bonded with steel, even if I cut at one location, other locations still already there is a compatibility, so there is no problem, right. So that is why again bonded system is better, but unbonded system also is good because the labor required and the time required for grouting and all, you get rid of it. And also tomorrow if you want to change the cable, it is easy for you to change the cable in an unbonded system, which is not possible in a bonded system. And okay, now let us go back to bonded system. In bonded system, tendons can be easily weaved, allowing for more efficient design approach, right, and higher ultimate strength due to bond generated between strand and concrete. And there are no long term issues with maintaining integrity of anchor or dead end, right. And here you see another example for two cases, bonded system and unbonded system. Now because again I have strain compatibility, I I don't have a localized failure in bonded system. The failure also tends to spread for a larger region, which is what as a structural engineer we want. We don't want to have a localized failure. The failure should not be localized to one particular location, right? So if you want to have a distributed damage, it's always better. So you get widespread cracks in case of a bonded system. But however, in case of an unbonded system, wherever you have maximum demand, that's where your cracks tend to localize. In that way, you get localized spread of cracks, which is also not a good thing.